Presenting on the differential power analysis testbed sponsored by Dr. Katz. Today we're going to talk about the basics of encryption, what a side channel attack is, and more specifically DPA, or differential power analysis. We're also going to talk briefly about the side channel evaluation system, which is currently the standard testbed, hardware and software based for this type of attack. And then finally we're going to finish with our proposed solution.
In symmetric key encryption, unencrypted data, or plain text, is combined with a secret key to produce encrypted data, or ciphertext. In the decryption phase, this ciphertext is combined with the same secret key to decode the data. This means that if an attacker is able to obtain the secret key, they can then read any data that was encrypted with that key. Encryption is seen in various different things in modern technology, on computers, on some credit cards, and also on a lot of smartphones. Most notably, the BlackBerry is known for encrypting its communications. There are about 41 million BlackBerry users, which is about 15% of the smartphone worldwide market share.
While designed to be mathematically secure against resistance to attack, a side channel attack can be used to crack the encryption key a lot faster. This is due to the fact that once the cryptographic algorithm is implemented on a physical device, an attacker could measure such things as power consumption, computational timing, acoustics, or electromagnetic emissions of the device to obtain the key. Our focus for our project is actually on differential power analysis, so taking power readings of the cryptological device. The measurements are taken via oscilloscope, and these traces are then used against a theoretical key guess file to obtain the key. Shown here is a power trace and a correlation from MATLAB showing that key 174 is the most strongly correlated to the actual key.
More specifically, our project focused on using DPA against the Advanced Encryption System, or AES. DPA works well against AES as it allows one to attack one byte of the key at a time, rather than trying to guess at the entire key. If we take, for example, AES using a 128-bit key, one would have to attack the entire key. One would have to account for 2 to the 128 different combinations, or about 3 by 10 to the 38 different scenarios. The age of the universe is only comparatively 4 by 10 to the 23 nanoseconds. Thus, if you ran one attack per nanosecond, it would take longer than the universe has existed to obtain the key through brute force. However, using DPA, the complex number of scenarios goes down to about 4,096, which is trivial in comparison. So background on AES, in 1997, the National Institute for Science and Technology decided that currently available encryptions were not strong enough and requested for a new algorithm. In 2001, the Rindall algorithm was selected to fill this need. AES is a symmetric block cipher that can both encrypt and decrypt using one secret key.
This is a flowchart of AES. As you can see, the plaintext enters at the top, goes through an initial round, and then through 9 intermediate rounds. Because of the iterative structure, this makes DPA significantly more effective. And then before proceeding through a final round at which the ciphertext is produced. This is an image of the Sasebo G2 board, which is the current hardware standard for differential power analysis. It breaks down with 2 FPGAs, a control and a victim. The control FPGA controls the victim FPGA as well as communication with the computer, and the victim FPGA simply runs the encryption. The basic system operation of this device is that the PC actually interfaces with the control FPGA, which then sends relevant data to the victim. The encryption is then run while connected to an oscilloscope. Should the oscilloscope's memory become full, the current encryption is ended, the oscilloscope memory is pulled, and the encryption begins anew until enough power traces, which are user-defined, have been obtained to make a correlation.
So Sasebo works well. However, it's limited because it's inflexible. You can only use the victims that they have a board for. They only offer 3 chips for victims right now: Vertex 2, Vertex 5, and Stratix 2. Our objective was to improve upon Sasebo by making a Sasebo-compatible generic device, essentially splitting Sasebo into 2. To do this, we used 2 separate FPGA boards. A control board which handled communications between the PC and the victim, and a victim board which ran actual encryption.
So from that, we came up with the following high-level system requirements. For our controller board, since the USB interface on the Nexus 2 uses a Cypress chip and the standard Sasebo board uses an FTDI chip, we would have to rewrite the USB interface module. We would also need to provide communications between the control and the victim board, as well as providing the actual physical connection between them. As part of that requirement, we needed to make it generic so that you could attack any device. So generic pins were added, as well as an external clock connection, so that you can clock either board at an external user-defined frequency. On top of that, we needed to modify the Sasebo PC-based control software as I mentioned before, the chipset was different, so the driver would not be compatible. This is a board-level design of our system, showing all of the necessary components that I just mentioned. The components that are highlighted in yellow are actually components that we had to change, modify, or completely write from scratch ourselves, whereas the blue modules were provided by the Sasebo code.
This is an in-depth look into our USB interface. As was mentioned, we had to rewrite the USB communication so it would work with our control board. The digital driver we had to use was designed to allow the PC to communicate directly with an onboard RAM, whereas the Sasebo is designed to just accept byte streams. So in order to interface these 2 protocols, we shrunk the RAM into just 2 address spaces, one for data coming from the PC and then streamed to the victim through the controller, and one for the reverse path. In order to handle control signals needed to synchronize the controller with the USB module, we added a synchronization controller. This is a picture of our bridge module, which we use to connect our victim and our controller. On the left and right, you see the Hyros FX2 connectors. And in the middle is our generic pinout, so you can connect it to any board you like. We have 40 input-output pins altogether, as well as an external clock. The C# control software can be represented as such with a high-level block diagram. The overlay again is parts that we had to modify and rewrite. The actual Digilant USB driver is provided in a C in C. Unfortunately, as you can see, the actual acquisition code is in C#, and while C and C# sound similar, they do not like to play nicely together. So an interface program was written in C++ to actually allow us to call an interface.
That makes sense.
I
had to do that.
So this is actually our communications test circuit, where we were able to verify so for our unit testing that we could test and see that were we getting communications. So we wrote some test software to interface with the Digilant USB chip, and then a Sasebo-like interface on the control FPGA across our bridge module, and then over to the victim FPGA, which simply inverted the bits, so XOR with FF, and then back again. This round trip actually utilizes 5 programming languages: C#, C++, C, VHDL, and Verilog, all the way across and then back again. The actual result was really simple. We just sent 6, 7, 8. It's really easy to see. So since it was inverted in signed integer notation, that will get us 249, 248, 247. And that's just in the console of Visual Studio, the output. So the results of our project were we actually were able to prove round-trip communications between from PC through USB to our control board through our bridge module to the victim. However, unfortunately, when we added the AES core that Sasebo uses on the victim, we were incapable of actually getting that AES core to provide any data back to our system. However, we did manage to trace down that the data is being sent through the control board to the victim board, so something is not mapping correctly on the victim board. So the data does not return to the control.
Our estimated overall cost was about $7,300. Most of that came from average annual wages for various code developers and very conservative man-hour estimates. We also had some plain hardware costs for the high-res connectors, PCB fabrication. We were able to save some money because the control and victim boards were donated for use in this project. Division of labor, essentially I was responsible for the hardware side of things, setting up the FPGAs and fabricating the bridge module, whereas my partner Patrick focused on the software aspect, primarily the waveform acquisition software. Lessons learned: if you didn't write the code, don't trust it. Since we were building on something that already existed, we had to reuse a lot of code that was already written. That introduced a lot of bugs that we did not expect in our design phase and was cause for most of our issues. Also, debugging takes a lot of time and should be a primary consideration when scheduling out your project. One issue we had in the earlier phases with trying to debug our communications is we didn't have the bridge module. To get around that, we made a mock-up bridge module, basically wire wrap communications. But wire wrapping doesn't really work too well in this instance. So this concludes our presentation. Thank you for your time.